Okay, so we're going to be looking at active filters here today, and something weird just happened there, in our labs. And let me finish drawing out this circuit here. We have an active filter here, and this active filter has a gain of 1. Now, active filters have some kind of op-amp in them, and an op-amp is considered an active device because it's made up of transistors. Now, you might say, okay, great, but why would I possibly want an active filter like this? Well, we have on the first stage here, I'll circle it here, kind of in some dotted lines. If I look at that portion right there, that looks just like one of our passive filters that we've had. And we're just feeding it into the positive terminal there. And then remembering for an ideal op-amp, whatever voltage is on the positive terminal is the same as the voltage on the negative terminal. And then that's tied directly to the output. So remembering for an ideal op-amp, V positive voltage at the positive terminal, I'll write it like this, voltage at the positive terminal is equal to the voltage at the negative terminal. And so, again, since Vn is tied to V out, V out is simply equal to Vn. But this is still a filter, because if I think about the transfer function, well, we said that V out is equal to Vn, but then because it's an ideal op-amp, that's equal to the voltage at the positive terminal. But then if I look here, the voltage at the positive terminal is the voltage across this resistor. And now I'm just going to do here where I have 1 over SC, and then just R, and doing a voltage division, V positive is equal to R over R plus 1 over SC times Vn, and then doing some algebra that I'm going to skip because it's essentially the same that we've done in another one. We get that V out is equal to, I should say V out over Vn, which is my voltage gain, is equal to S over S plus 1 over RC. And if we remember our transfer functions from our passive filter, this was actually a transfer function for a high-pass filter. And the cutoff frequency here is going to be the exact same. So 1 over RC if we have it in radians per second, or if you're wanting it in frequency in hertz, it would be 1 over 2 pi RC. Now, to get a low-pass filter, we are literally, just like we did with the passive filters, switch where the capacitor and resistor are located, and that will give us a low-pass filter. But you might say, okay, well, what was the point of putting this op-amp in here? Well, there's several good things about this. Remember, we were concerned about loading effects on the next stage. If we were trying to combine amplifiers together, we had loading effects that we had to be concerned about because we had to make the resistors like 10 to 100 times bigger than the previous stage, or we'd have loading effects. Well, op-amps tend to have low output impedance and high input impedance. So loading effects of cascaded filters can be ignored. So that means we don't have to worry about loading effects, and if I want to cascade these together, I literally just cascade them together without worrying about the loading effects. Now, you might say, okay, it has a gain of 1, and you might say I tied this negative terminal directly to the positive terminal here. I can actually get gain out of this. So there's another configuration that we can write these in. So if we draw the circuit now like the following, if I can draw decently here, plus, minus. So I'm still going to draw my high pass filter. So I've got my resistor here, R. I've got my capacitor here, C. This is my input. And I'm going to put an output here. But this time what I'm going to do is I'm going to put another resistor here tied to ground. I'm going to call this R1. Put another resistor there. And call this R2. Now, if we look at this transfer function, we can actually do a nodal analysis at this point right here. And we still have, note that we still have that Vn is equal to Vp. We still have that, okay? So that's not different. But now we don't have that V out is equal to Vn because of these resistors. But if I do a nodal analysis at that dot there, what I do have is I have that Vn minus V out over R2 plus Vn over R1 equals 0. Because again, no current is going to go up into the op amp because we assume these are ideal, and so the current going into the op amp is 0. Now, just kind of simplifying this a little bit, I'll have R1 times Vn minus V out plus R2 Vn equals 0. And so we'd have R1 Vn plus R2 Vn is equal to R1 V out. So we're going to divide everything by R1. So we have Vn plus R2 over R1 Vn is equal to V out. Or we have 1 plus R2 over R1 Vn is equal to V out. Now, my Vn is still equal to Vp, which is going to still be given by, well, technically it's given by this equation here. So what I'm going to have, though, is I'm still going to have here that Vn is equal to S over S plus 1 over RC times Vn. So then I get here, substituting this in, right in here, what I wind up getting is that I have V out is equal to S over S plus 1 over RC times 1 plus R2 over R1. Times Vn. So my voltage gain then, which is V out over Vn, is equal to S over S plus 1 over RC times 1 plus R2 over R1. Now there's some important things we should highlight here. This portion gives me my cutoff frequency, and the cutoff frequency is still omega c is equal to 1 over RC, or Fc is equal to 1 over 2 pi RC. But then this term right here gives me my gain. If I could spell that word. Gain. So in other words, I can filter and amplify at the same time. So I can be doing a high pass filter while I'm amplifying the signal at the same time. So I can be, for instance, if I have a cutoff frequency, let's say I have a cutoff frequency equals, let's just say 10 kilohertz. So I have my cutoff frequency of 10 kilohertz, but then I can also amplify signals above 10 kilohertz at the same time. Now, one final thing we should note here, if we're doing amplification here, is that the minus 3 dB point is actually equal to the max of the voltage gain minus 3 decibels. So it's not necessarily negative 3 decibels. And let's do a quick example to illustrate that. Let's suppose we have a gain of 20. I don't care what the cutoff frequency is, just a gain of 20. Now to convert the gain to decibels, the formula here is decibels of my gain is equal to 20 times the log base 10 of the absolute value of our voltage gain. So for this one, this would be equal to 20 times the log of 20. And if I do that on my calculator, I get that this is 26 point, well, it's just 26.0, so we'll just say 26 decibels. So the minus 3 dB point is 26 minus 3, which would be 23 decibels. So when we're saying the minus 3 dB point, it's not negative 3. It's minus 3 from whatever the maximum is. So in this case, my minus 3 decibel point would be 23 decibels is what I would have at the cutoff. So what's interesting about these is while we're still filtering, the signals that we're filtering off are still also getting amplified as well. So it's an interesting thing that happens with filters. One of the reasons why you typically want to go higher than a first order filter. But those are for later courses in the electrical engineering program. We're just starting with first order filters. All right, so that gives you kind of a good idea on how these filters work and what you'll need in order to do this week's and next week's lab.